In the previous part of acid-base, we studied the pH calculation of monoacid or monobase, strong or weak. In this part, we will study the pH calculation of a mixture of acids or mixture of bases, and we have several cases to treat if the acids are weak or if the acids are strong, or if we have one strong plus one weak. We will also study the pH calculation of the polyprotic acid H2A and H3A, and the pH of the polyprotic base. We will consider only one example, which is A2-. pH calculation of a mixture of strong acid HA1 and another strong acid HA2. Suppose we mix HA1, a volume V1 of concentration C1, with HA2 of volume V2 and concentration C2. In this case, we don't have reaction, since no reaction between two acids which are both donors. Dilution of HA1 and HA2 occur in the solution after mixing. So we have to calculate the new concentration of HA1 and HA2 in the solution at T equals 0. And this is the solution dilution equation. The initial concentration times the initial volume is equal to the concentration final times V final. In this example, the volume of the solution V final or V total is equal to V1 plus V2. The new concentration of HA1 in the solution is equal to C1 V1 divided by the volume final, V final equal V1 plus V2. And the new concentration of the acid 2 in the solution by the same way is equal to C2 V2 divided by V final. Since HA1 and HA2 are strong acids, they will dissociate completely to HCO+. So HCO+ provided by HA1 is equal to the concentration of HA1 in the solution, and HCO+ 2 provided by the acid HA2 is equal to the concentration of HA2 in the solution. And pay attention that HA1 and HA2 in the solution are the concentrations after dilution. The concentration of HCO+ total is equal to the concentration of HCO+ provided by the first acid plus HCO+ provided by the second acid, and HCO+ total in this case is equal to C1 V1 divided by V final plus C2 V2 divided by V final. So we know now the concentration of HCO+ total, since C1 V1, C2 V2 and V final are given. So we calculate pH equal minus log concentration HCO+ in the final solution, and we find the pH of the mixture of two strong acids. An application, for example, a solution is prepared by adding 50 milliliter of 0.05 molar HCl, which is a strong acid, since no Ka value given, to 150 milliliters of 0.1 HNO3 nitric acid. It's also a strong acid, since no Ka given at 25 degrees. Calculate the concentration of all species in the solution and deduce the pH of the final solution. First of all, HCl and HNO3 are two strong acids, so we don't have reaction between them. What would happen when we mix HCl with HNO3? We have to take into consideration the dilution factor. So the new concentration of HCl in the solution is equal to 0.05 times 50 divided by the V total, which is 150 plus 50 equal to 100 ml. So this is the new concentration of HCl. By the same way, the new concentration of nitric acid in the solution after dilution is equal to 150 times 0.1 divided by V total, which is 200 ml. So we obtain HCO plus equal 0.087 molar, which is the addition of HCO plus of HCl and HCO plus of HNO3, and pay attention for the to calculate the concentrations after dilution. If we know HCO plus, we can calculate OH minus HCO plus times OH minus equal KW. The concentration of Cl minus is equal to the concentration of HCl in the solution after dilution. By the same way, NO3 minus is equal to the concentration of HNO3 in the solution after dilution. Calculation of the pH of a mixture of strong acid HA1 and the acid HA2 is weak. So we mix strong acid HA1 volume V1 C1 with weak acid HA2 of volume V2 and concentration C2. So the total volume of the solution is V1 plus V2. When we mix HA1 and HA2, we don't have reaction because they are two acids, and we have to take into consideration the dilution effect. HA1 is a strong acid, so it will dissociate completely to HCO+. HA2 is a weak acid, so its dissociation to HCO+ is partial. What is the concentration of HA1 and HA2 in the solution after mixing? HA1 in the solution is equal to the initial concentration C1 V1 divided by V final, and HA2 by the same way equal C2 V2 divided by V final. We saw in the case of the strong acids, the HCO plus total was equal to HCO plus provided by the two acids, since the dissociation is complete. But in this case, we have one acid strong and one acid weak. So how to calculate the concentration of HCO plus total in the solution? The weak acid, the presence of the weak acid does not affect the dissociation of the strong acid, since this dissociation is complete. But the presence of the strong acid will affect the equilibrium dissociation of the weak acids. So the strong acid dissociates completely to HCO+. The weak acid will react with water to dissociate partially into HCO+ and A2-. At T equals 0, the initial concentration of HA2 equals C2V2 divided by V final. At T equals 0, the concentration of HCO plus is not equal to 0, since we have, with the weak acid, initially we have a strong acid of concentration C1V1 divided by V final. So at T equals 0, the concentration of HCO plus is the concentration of the strong acid after dilution, C1V1 divided by V final. A2 minus at T equals 0 equals 0. HA2 will dissociate till the equilibrium, and at equilibrium, HA2 concentration equals C2V2 divided by V final minus X, C1V1 divided by V final plus X, and A2 minus is equal to X. We know Ka of the acid HA2 and Ka equal HCO plus at equilibrium times A2 minus at equilibrium divided by HA2 at equilibrium. So we can calculate K from the expression of Ka. Then the total concentration after calculation of X, the total concentration of HCO plus in the solution is equal to C1V1 divided by V final plus X. So we know now the concentration of HCO plus in the solution. We apply pH equal minus log HCO plus in the solution, and by this way we calculate the pH of the mixture of strong acid with a weak acid. To note that in most cases, when we have a strong acid and weak acid, and the concentrations are close in the solution, we neglect the weak acid, so the strong acid will set the pH value. By other word, when you calculate X, you will find that X is negligible with respect to C1V1 divided by V final, so HCO plus in the solution, which is equal to C1V1 divided by V final plus X, will be equal only to C1V1 divided by V final, and this is the concentration of HCO plus provided by the strong acid. So the strong acid set the pH value. Suppose we have now two weak acids and we want to calculate the pH. So after mixing HA1 and HA2, the weak acids, we will have dilution, and we will suppose that the concentrations of these two acids in the solution after dilution is C1 and C2 respectively. So what would happen when the two weak acids are mixed together? HA1 will dissociate in water to give HCO plus and A1 minus, and this reaction is partial since HA1 is weak acid, and K for this reaction is equal to Ka of the couple HA1 A1 minus. So K of this reaction equal Ka equal A1 minus concentration times HCO plus concentration divided by the concentration of HA1, and all these concentrations are equilibrium. By the same way, HA2 dissociates in water partially to give HCO plus and A2 minus. K for this second reaction is equal to K prime A of the couple HA2 A2 minus. So how to calculate the HCO plus total in the solution? We return to our study in the introduction, and we saw when we have two reactions in the same reaction system, we have to study their sequence. And to study the sequence of two reactions, we compare their value K of the reactions, since we have the same stoichiometry. The dissociation of HA1 and HA2 in water have the same stoichiometry. So to compare the sequence of these two dissociations, we have to compare Ka and K'A. We have two cases. The first, if Ka is greater or equal 1000 times K'A. To note that in some books, they use the order 1000, and in other books, especially the French books, they use the order 100. In our course, we will use the order 100. So when we say Ka greater or equal 1000 times K'A, it's the same if we consider that Ka is greater or equal 100 times K'A. So both cases are used, but in our course at the university, we use the order 100. So if Ka is greater 100 times K'A, that means the reaction 1 starts, ends, then the reaction 2 starts. And in this case, we consider only the dissociation of HA1 in water, so we consider only equilibrium 1. HA1 acid is then much stronger, so as we said, we neglect the presence of HA2, and the problem amounts to calculating the pH of a solution of the weak acid HA1. So the problem HA1 plus HA2, two weak acids, is the same as we said in this case, calculate the pH of the solution of HA1. The second case, when Ka of reaction 1, which is equal to K, is not greater or equal to 100 K'A of reaction 2. So we have to consider the two reactions. These two reactions start at the same time, but with different advancement. Write the relation that express the electroneutrality, and to note, in any solution, the principle of the electroneutrality is applied. So what are the species when we mix HA1 and HA2? We have HA1 remained, A1 minus formed, HA2 remained, A2 minus formed, and we have H2O plus in the solution. So the principle of the electroneutrality, the quantity of charge positive is equal to the quantity of charge negative, will give concentration HCO plus equal 1 times A1 minus plus 1 times A2 minus plus 1 times OH minus. So HCO plus concentration equal A1 minus concentration plus A2 minus concentration plus OH minus concentration in the solution. And since we have two acids, so the medium is acidic, so OH minus can be neglected in this case, and we will obtain H2O plus equal A1 minus in the solution at equilibrium plus A2 minus in the solution at equilibrium. We return to the expression of Ka and K'A. A1 minus at equilibrium equal Ka HA1 divided by HCO plus, and A2 minus at equilibrium in the solution equal K prime A HA2 divided by HCO plus. And since HA1 and HA2 are in general weak acids of weak strengths, so HA1 at equilibrium is practically the initial concentration C1, and HA2 at equilibrium is practically the initial concentration C2 after dilution. So the expression HCO plus concentration equal A1 minus concentration at equilibrium plus A2 minus concentration at equilibrium will be equal to Ka C1 divided by HCO plus K prime A C2 divided by HCO plus. So HCO plus square equal Ka C1 plus K prime A C2, and HCO plus in the final solution will be equal to radical KaC1 plus K prime A C2. Knowing HCO plus in the final solution, we can calculate that pH equal minus log HCO plus equal minus log radical KaC1 plus K prime A C2. Parts of acid-base, we studied the pH calculation of monoacid. A strong acid, HA for example, release 1 mole HCO plus, and a weak acid, HA, release less than 1 mole HCO plus. By definition, a polyprotic acid is an acid that can donate more than 1 proton HCO plus per molecule to an aqueous solution. Consider, for example, H2A. H2A can release maximum 2 mole of HCO plus if H2A is a strong acid, and if H2A is a weak acid, it will release less than 2 mole HCO plus, but more than 1 HCO plus per molecule. So H2A is a diprotic acid. What would happen when H2A is weak diprotic acid in water? H2A will dissociate in water partially to give HA minus and HCO plus. Then HA minus react with water to give A2 minus and HCO plus. The couple involved in the first reaction is H2A, HA minus, and in the second is HA minus, A2 minus. K of the first reaction is equal to Ka1, and K of the second is equal to Ka2. And pay attention, always Ka1 is greater than Ka2. That means the first acidity of diprotic acid is stronger than the second acidity of this acid. The objective is to calculate the pH of the solution when we put H2A in water. So we have to calculate the concentration of HCO plus total provided by H2A and HA minus. So to study or to calculate the concentration of HCO plus total in the solution, we have to study the sequence of these two reactions. And these two reactions are of same stoichiometry, so the value of K can be compared, or by other word, the value of Ka1 and Ka2 can be compared to know the sequence of these reactions. If Ka1 is greater 100 times than Ka2, that means we consider only the first reaction and we neglect the second. So in this case, the pH of H2A solution is equivalent to the pH of H2A by supposing H2A is a weak monoacid as HA. So now we return to the calculation of the pH of weak acid. We have to know what is the initial concentration of H2A used and to compare this concentration to the value Ka over 10 and 100K. If the initial concentrations of H2A is greater than or equal 100K, we apply the formula pH equal half pKa minus half log C, and pay attention what value of Ka should be used, Ka1 or Ka2. We have to use Ka1 because we neglected the reaction 2, so pH equal half pKa1 minus half log C. And if the initial concentration of H2A is less or equal Ka over 10, we apply pH equal Pc. And if this concentration is in the domain Ka over 10, 100K, we apply the relation of second degree HCO plus square plus Ka1 HCO plus minus Ka1C equal to 0. As an application of pH of a weak diacid, determine the pH of all species in a 0.5 molar carbonic acid H2CO3 solution and given Ka1, Ka2. When we put carbonic acid in water, we have two reactions, H2CO3 to HCO plus HCO3 minus, and K of reaction 1 is equal to Ka1. Then HCO3 minus continue its partial dissociation in water to HCO plus and CO3 2 minus, and K of the second reaction is equal to Ka2. Since the question is to determine the pH of all species, that means we have to calculate also the concentration of this species, not only the pH. So the species present are H2CO3, noted H2A, and HCO plus, OH minus, HA minus, and A2 minus. We have to compare Ka1 and Ka2. Ka1 is greater 100 times than Ka2, so H2A can be considered as weak monoacid. In other words, we use only reaction 1 and we neglect the reaction 2. So the pH of H2A is the pH of weak monoacid. We have to compare the initial concentration of H2A to the value of Ka1. Comparing C0 and Ka1, we will find that C0 greater or equal 100 Ka1. So H2CO3 can be considered as weak monoacid of weak behavior. And in this case, pH equal half pKa1 plus PC0. So you calculated the pH equals 3.34. If we have another question to calculate the concentration of all species in solution, so HCO plus equal HCO3 minus equal 10 to the power minus pH, so 10 minus 3.34 equal 4.5, 10 minus 4 molar. HCO plus times OH minus equal Kw, so OH minus equal Kw divided by HCO plus equal 2.2 10 minus 11. We have to calculate the concentration of H2A remained. The concentration of H2A remained equals C0 minus X. C0 minus X, so equals 0.5 minus X, which is the concentration of HCO plus or HA minus. So H2A is practically 0.5. The dissociation is very, very weak. To calculate A2 minus, we use the expression of Ka2. Ka2 equal HCO plus A2 minus divided by HA minus concentrations at equilibrium. And since H plus is supposed equal to HA minus, so Ka2 equal A2 minus equal 5.6 10 minus 11. So in this application, we calculate the pH of the solution and the concentrations of all species present when we put H2A in solution. To note that H plus has two sources and HA minus has one source. The source of HCO3 minus is only the dissociation of H2CO3, but the source of HCO plus is the dissociation of H2CO3 and the autoionization of water. But in this problem, we neglect the autoionization of water. For this reason, H plus equal HA minus. Calculation of pH of polyprotic base, we use the same analogy as the polyprotic acid, but replacing the pH by POH and Ka by Kb. So what is the definition of a polyprotic base? Is a base that can donate more than one OH minus according to Arrhenius definition, or can receive more than one HCO plus according to Lewis definition per molecule to solution. Consider a diprotic base A2 minus. What would happen when A2 minus is put in solution? We have two reactions. A2 minus in water dissociate to HA minus and OH minus, and K of reaction 1 is equal to Kb1. Then HA minus continue the dissociation to H2A and OH minus, so K of reaction 2 is equal to Kb2. And always we have Kb1 greater than Kb2. That means the first basicity of A2 minus is stronger than the second. To note that the couple involved in reaction 1 is HA minus, A2 minus, and the couple involved in reaction 2 is H2A, HA minus. So reaction 1 is characterized by Kb1, and for the couple HA minus, A2 minus, we have a value Ka2. So Kb1 is versus Ka2, and Kb1 times Ka2 is equal to Kw. Ka of the couple and Kb of the same couple are related according to Kw. In reaction 2, the couple involved is H2A, HA minus, characterized by Kb2. And H2A, HA minus has a value Ka1. So Kb2 is versus Ka1, and Kb2 times Ka1 equal Kw. This is a common mistake of the student. The student always write Ka1 times Kb1 equal Kw, and this is incorrect. Pay attention for the relation between Kb and Ka of polyprotic acid or polyprotic base. The objective is to calculate the pH of the solution when we put A2 minus in water, so the pH will be basic. We have to calculate the concentration total of OH minus, so we have to compare the sequence of these two reactions. By the same analogy as the polyprotic acid, if Kb1 is greater 100 times Kb2, so we neglect the second basicity and we consider only the dissociation of A2 minus to HA minus, and in this case, the POH of A2 minus, I prefer to use POH since we are working with bases. So the POH of A2 minus will be equivalent to POH of A2 minus considered as weak mono base. As weak mono base, we have to correct this is weak mono base. So only Kb1 is considered. We return to the interval of the weak base. We compare the initial concentration to Kb1. If the initial concentration is greater 100 times Kb1, we apply POH equal half pKb1 minus half log C. If the initial concentration is less than Kb1 over 10, we apply POH equal Pc. And if it's in the domain Kb1 over 10, 100 Kb1, we solve the equation, quadratic equation, HO minus square plus Kb1 OH minus Kb1 C is equal to 0. So we find OH minus then POH. After we find POH is related to pH. POH plus pH equal pKw, so we can find the pH of the polyprotic base. pH calculation of triprotic acid H3A. Consider a solution of phosphoric acid H3PO4. When we put phosphoric acid in water, we have three dissociations. The first corresponds to the couple H3PO4, H2PO4 minus, and characterized by K of the reaction equal Ka1. H2PO4 minus continue dissociation, so reaction 2 corresponds to the couple H2PO4 minus, HPO42 minus, characterized by K of the reaction equal Ka2, and HPO42 minus dissociates to HCO plus PO43 minus, and the couple involved is HPO42 minus, PO43 minus, K of the reaction is Ka3. To calculate the pH of the solution obtained when we put H3PO4 in water, we have to calculate H3O plus total. So we have to study the sequence of these reactions. So to compare Ka1, Ka2, and Ka3, since we have the same stoichiometry for the three reactions. Comparing Ka1 and Ka2, we found that Ka1 greater 100 times Ka2, so we consider only the first reaction or the first acidity, and we neglect the second and the third. So the pH of phosphoric acid in water is as the pH of H3PO4 that dissociates to H3PO4 and H2PO4 minus. So H3A can be considered as weak monoacid. So now we return, the problem returns to the calculation of the pH of weak monoacid. We have to compare the initial concentration of phosphoric acid with the value Ka1 over 10 or 100 Ka1. If the concentration of phosphoric acid initial is greater 100 times Ka, we apply the pH equal half pKa1 minus half log C. If the initial concentration less than Ka over 10, we apply pH equal Pc. In the interval Ka over 10, 100 Ka, we apply the second degree equation. We find HCO plus acceptable, then pH. So we have the same strategy as the weak diacid, but in this case we have another third acidity. The relation between Ka and Kb of triprotic acid, pay attention that Ka1 corresponds to Kb3, so Ka1 times Kb3 equal Kw. Ka2 corresponds to Kb2, if you look to the couples, okay, Ka2 corresponds to Kb2, and Ka2 times Kb2 equal Kw, and Ka1 is related to Ka3 is related to Kb1, Ka3 times Kb1 equal Kw. And as a conclusion, Ka1 is the greatest in the Ka value, so the first acidity is the strongest. Kb1 is the greatest in the family of Kb, so the first basicity is the strongest. To note also that Ka1 corresponds to the first acidity of HCpO4, Ka2 to the second acidity of HCpO4, Ka3 to the third acidity of HCpO4, Kb1 to the first basicity of PO4 3-, Kb2 to the second basicity of PO4 3-, and Kb3 to the third basicity of PO4 3-.